Hi all, welcome to my channel and today we are going to discuss about the dark slip curve and stiffness bar and the problems of the dark. Okay. So in the previous class we have discussed about the condition for dark and the running condition and the maximum dark equation, the dark equation in the running condition, okay, and the rotor current EMF under the running condition. So today we are going to discuss about how to draw the dark slip curve from three-phase induction motor and what is impedance what and some of the problems on the dark. Okay, what is dark slip characteristics under load? As stated earlier, stable operation of an induction motor lies over the linear portion of its dark slip curve, and the slope of the straight line depends mainly on the rotor resistance. Higher the resistance, sharper the slope. This linear relationship between the torque and speed, which is showing in the figure 1, enables us to establish a very simple equation between different parameters of an induction motor. So this is a torque slip curve. In the y-axis we took torque, and in the x-axis we took speed, and we can even take a slip. Okay. Here, initial at initial conditions, that is at standstill condition, standstill condition, that is n is equals to 0, where here at this point s will be equal to 1, because we know that and its synchronous speed s is equals to 0. Okay, so here s formula is equals to ns minus n divided by ns. Okay, as n is equals to 0, so ns divided by ns is equals to 1. So here at standstill s is equals to 1. Okay, so here they took some tasks, and the line this is showing, this is called a starting torque, and from here the curve, as the speed increases from 0, the torque will be in such direction, and we can say as the speed increases, the torque will depends upon slip, so the slip decreases, it will be increased at a till certain speed or a certain slip. After that it will gradually decrease. When it reaches to ns, then the torque is equals to 0. Why the torque is 0 at ns? As if the rotor reaches to ns, EMF will be equal to 0. When there is no EMF, there is no current and there is no torque. Okay? So here if we observe, there is torque 1 and torque 2. So depending upon two different resistors, the torque is different. So here it is showing it is a maximum torque. Maximum torque. Okay. And this graph gives us here in this x-axis, it is a current, some percentage of motor full load current, and torque, it is a percentage motor full load torque. Okay. And here it is a rotor speed, it is in percentage of full load speed. See here, The torque it is given here, but it is also in x-axis at this side only. Okay. So here the torque is increasing from starting torque to it is increasing, and at the time it has reached to the maximum torque and it got decreasing. Okay. So, and if we observe here, it is 3 times of full load current. At 3 times, 4 times of full load current, the starting torque is there, and here full voltage stator current. So the stator current will be at the when speed is zero, it is high, and it decreases as the speed increases, and it will reach to zero when it reaches to ns. The rotor reaches to ns. Okay, and this is a sample load torque curve. Okay, and yes, here the torque versus speed, and this is a magnet, and this is a measured value. So whatever we have seen before, same thing like see at the starting, and again it is increasing and it is decreasing. Okay. So this is somewhere experimental graph. So the previous, so the parameters under two different load conditions are related by the equation. That is S2 is equals to S1 into T2 by T1 into R2 by R1 into V1 by V2 whole square. The only restriction in applying the above equation is that the new torque T2 must not be greater than T1 and V2 by V1 whole square. In that case, the above equation yields an accuracy of better than 5%, which is sufficient for all practical purpose. So the complete torque and speed curve. So we have already seen that a three-phase induction motor can be run as a motor when it takes electrical power and supplies mechanical power. And the direction of the torque of the rotor rotation, are in the same direction, and the same machine can be used as a synchronous generator when driven at a speed greater than synchronous speed. So in this case, it receives mechanical energy in the rotor and supplies electrical energy from the stator. And the torque and speeds are opposite direction. And the same machine can also be used as a brake during the plugging period. So the three modes of operation are depicted in a torque and speed curve in figure 2. So this is a figure 2. This figure what it is telling, so a motor, a machine can be run in three modes here. It can be run as a motor, and it can be run as a generator, and it can be used as a brake mode. Okay, so here, see, this is a torque and speed equation. So we know this is only like this only the torque is falling. Okay, and here we observe the speed is from 0 to ns, and after ns till 2 ns, this same motor will run as a asynchronous generator, and the graph will be quite opposite as a motor. Okay, and in the negative speed, the negative speed, that this motor will run as a in a braking mode. Okay, in this mode, the power input will be taken, that the electrical power it will be taken, and the output will be mechanical power. Here the mechanical power will be taken and the output will be the electrical. So, induction motor torque equation we have already seen, but we will discuss again. The gross torque Tg developed by an induction motor Tg is equals to P2 by 2 pi ns, which is 2 pi ns by 60, which is equals to P2 by 2 pi, which is equals to 9.55 P2 by ns. And as seen from I2 is equals to S into E2 by under root of R2 square plus SX2 square, which is equals to S into K E1 by under root of R2 square plus SX2 whole square, where K is a rotor by stator turn ratio per phase, and P2 is equals to, this is a power input, which is equals to 3 into S square E2 square R2 divided by R2 square plus SX2 square into 1 by S, which is equals to 3 into S E2 square R2 divided by R2 square plus SX2 square. And also P2 is equals to 3 into S square into K square E1 square R2 by R2 square plus SX2 whole square into 1 by S. So the total P2 is equals to 3 into S K square E1 square R2 divided by R2 square plus SX2 whole square. And the Pg is equals to the power into P2 divided by 2 pi ns, which is equals to 3 by 2 pi ns into S into E2 square R2 divided by R2 square plus SX2 square, substituting P2 directly here. So this is in terms of E2, and we can get in terms of E1 also. So here this will become S into E1. Okay. Here E1, E2, R2 and X2 represents the phase values. In fact, 3 into K square is equals to K is called the constant of the given machine. Hence, the above torque equation may be simplified to Tg is equals to K into S E1 square R2 divided by R2 square plus S into Sx2 whole square. So what is the synchronous one? It is clear from the above equation that torque is proportional to the rotor input. By definition, the new unit of torque is instead of the force at radius. So we can say that the rotor torque equals to the rotor input. The new unit is synchronous watt. So when we say that a motor is developing a torque of 1000 synchronous watt, we mean that the rotor input is 1000 watts and that the torque is such that power developed would be 1000 watts provided the rotor were running synchronously and developing the same torque. Or synchronous watt is that torque which at the synchronous speed of the machine under consideration would develop a torque of 1 watt, power of 1 watt. So, rotor input is equals to torque into 2 pi ns. The torque is equals to rotor input divided by 2 pi ns. Speed is equals to 1 by omega s ns by n into Tg, which is equals to 1 by omega s into ns by n into T. So synchronous wattage of an induction motor equals the power transferred across the air gap to the rotor and the torque in synchronous wattage. So therefore, the torque in synchronous wattage equals to rotor input, which is equals to rotor copper loss by S, which is equals to gross output power, that is Pm by 1 minus S. So obviously at S is equals to 1, torque is in synchronous watt equals to the rotor copper losses becomes at standstill, entire rotor input is lost in copper losses. So now we'll see some of the problems. So here, problem number 1. So we have to first of all we need to analyze the problem. So study it, analyze it, and make the note of all the given data and make the note of that what we do find out. Okay? Fine. Here, a 6-pole 50 hertz three-phase induction motor has rotor resistance and standstill rotor reactance of 0.03 ohms and zero point 0.1 ohms per phase respectively. Calculate the value of external resistance to be connected in the rotor circuit to obtain 80% of the maximum torque at starting. So here the given data is P is 6 volts, X is equals to 50 hertz and it is a three phase, and the given R2 is equal to 0.03 ohms and X2 is equal to zero point 0.1 ohm, and they asked us to find out what is the external resistance which is added to the rotor to get the maximum starting torque which is of 80 percentage. No. So here starting torque is 80 percentage of the maximum torque. So in order to get the starting torque is 80 percentage of maximum torque, what they are doing, they are adding an external resistance. So adding of external resistance is only possible in slipping induction motor. So this is a slipping induction motor problem. Okay. So write down all the given data. Yeah. Yes. So starting torque is equals to 80 percentage of maximum torque. So we know even the formula also. So TST is equals to 0.8 according to this. And the ratio of starting to maximum torque is, so this is a formula, TST divided by T maximum is equals to TE divided by 1 plus H square. So this we know that is 0.8 which is equals to TE divided by 1 plus H square. And the A is the slip. So solving this equation, we will get a square minus 2.5a plus 1 is equals to 0. So a is equals to 0 or 0.5. So the smaller value of a must be selected. So we will get always, if it is an equation in this format, then we will get always two values. So we have to choose only the smallest value. So a is equals to 0.5 because slip won't be 2. If it is slip is 2, then it is acting as a generator. Now we are taking only the motor, so motor will be only from 1 to 0. So A is equals to 0.5. So we know this is a equation of solving this, that is so minus of minus b plus or minus under root of b square minus 4ac divided by 2. So we got A value. So now we have to find out the external resistance. So let R be the external resistance, then the total resistance will become R2 plus R and will be the total resistance and the ratio of rotor circuit standstill resistance, that is A is equals to R2 plus R divided by X2, which is equals to 0.03 plus R divided by zero point 0.1, which is equals to 0.5. So we know that A, the slip, is equals to R resistance divided by the reactance here. So what is the total resistance? That is R2 plus R divided by X2. So here 0.03 plus R divided by zero point 0.1. So we can get R directly. Then substituting the value, then R we will get 0.02 ohms. So the external resistance what we are adding to the actual resistance is 0.02 ohms. So this is about the problem and how to solve the problem. This is a way. And we will see the next problem, the second problem, that a 4-pole 50 Hz 7.46 kilowatt motor has a rated voltage and a frequency and a starting torque of 160 percentage and a maximum torque of 200 percentage of full load torque. So determine full load speed and speed at maximum torque. Now, so according to this formula, they ask us to find out a full load speed and find out the speed at which the maximum torque will occur. And the given data we have given the starting torque is 160 percentage and the maximum torque is 200 percentage of full load torque. Okay? And the given data number of poles P is equals to 4, frequency is 50 Hz, and uh, starting torque is equals to 160 percentage of full load torque and maximum torque is equal to 200 percentage of full load torque. So we do that starting torque divided by full load torque is equals to the formula already. So here the starting torque divided by full load torque is 1.6 and maximum torque divided by full load torque is equals to 2. So starting torque by full load torque is equals to 1.6 by 2, which is equals to 0.8. So we so starting torque by T maximum is equals to 2A by 1 plus A square. We know already. Okay. So and we got it is 0.8. So directly we are substituting the 0.8 at this, and now we have to find out A value. So here this is an equation. So by substituting minus b plus or minus in the root of b square minus 4ac divided by 4a. In that equation, if we substitute, we will get a is equals to 0.02. We will get two values. We have to select only the value as like the before example. Okay? And this is full load target full load divided by the T max, which is equals to UAS. So here UAS divided by A square plus S square, which is equals to 1 by 2. So this is full load means this is 100 and this is 2. So we know what is A. Okay. So as we know A, we can find out the slip at full load. So substitute it A in this formula. So we will get itself SF. That is a full load slip. So full load slip is 0.01. So synchronous speed is equals to 1500 rpm according to the formula 120 f by p. If we substitute the values which are given values, then we will get n is equals to 1500 rpm and the full load speed is equals to n into ns divided by 1 minus slip at full load is equals to 1500 into 1 minus 0.01. Then we will get 1485 rpm. So this is a full load speed. So when there is a full load, the speed of that motor is 1485 rpm. So now we have to find out the slip at the maximum torque. So maximum torque, what is the slip? So slip at maximum torque is equals to n is equals to ns into 1 minus slip at the maximum. So what is the slip at the maximum torque? That is 0.04. So 1500 into 1 minus 0.04, which is equals to 1440 rpm. This is the speed at the maximum torque. So this is how to solve the problems. So these are the only the two examples so that you could able to understand easily. So make sure that you have to practice more problems. Then you will get you will you will be able to solve the problems very easily. The efficiency and power factor of squirrel cage induction motor increases in proportion to the efficiency. Thank you. Hope you have understood today's session. So we will meet in the next session.